Metrology is the basis of science, engineering, and technology. This year, 2019, the SI base units have been redefined in terms of fundamental physical constants and the immutable properties of atoms. The revolution in cold atom physics that we've experienced has enabled the use of single atoms as high-precision sensors. For example, cold atoms are used to define time, enabling the GPS monitoring system. They've been used for gravitational field measurements, acceleration measurements, and determinations of electric and magnetic fields. Vacuum metrology, on the other hand, has lagged behind this development. Since the first atom trapping experiments, it's been observed that the trap lifetime is limited by collisions between trapped atoms and background particles that impinge upon them. In 2010, we formulated a method to determine pressure accurately for measurements of trap loss. Namely, the loss of atoms from a trap can be described as the product of the background particle density impinging on the trapped atoms times a velocity average cross-section. Key to this method was our demonstration that the velocity average cross-section is trap depth dependent. Not every collision leads to trap loss. Understanding this relationship makes it possible to extract accurate measurements of density.
One of the principal limitations of this method is that the collision cross-section is unknown and difficult, if not impossible, to calculate from first principles. In this paper, we report the solution to this problem. It exploits a universal law of collisional physics. This law can be thought of as a manifestation of the Heisenberg uncertainty principle, which defines a characteristic energy scale set by the localization of the sensor atom by the collision, determined by the total collision cross-section. The velocity average loss cross-section versus trap depth varies from species to species. However, the shape of each curve is dictated by a single parameter, the loss cross-section at zero trap depth. Rescaling both axes by this parameter reveals the universal shape for van der Waals collisions. This relationship allows the collision cross-section to be determined experimentally without reference to prior experimental work or theoretical calculations.
Then the next question is how we're going to use cold atoms to measure the pressure in the vacuum and test this universal law.
The experiment apparatus consists of rubidium source that is separate from and provides a constant rubidium vapor. The rubidium atoms are first loaded into a two-dimensional magneto-optical trap. The atoms in the 2D mass section are then propelled towards the 3D mass region using a horizontal laser beam, which we call the push beam. All the pressure measurements happen in the 3D mass region that are directly compared with an ionization gauge calibrated by National Institute of Standards and Technology. The measurement sequence starts by loading rubidium atoms into the 3D mass section with the help of lasers and the magnetic field. We then transfer rubidium atoms into a pure magnetic trap by turning off the lights and increasing the magnetic field by about a factor of 20. The cold atoms will be held inside the magnetic trap and they will collide with background particles. After a amount of holding time, we turn the light back on and count how many atoms left. We repeat this sequence many times with different holding times, then we can extract the decay rate of the cold atoms.
This is a breakthrough in the use of cold atoms as a pressure sensor, especially so because it enables the measurement of absolute pressure, or flux, for any species. This is a new definition of pressure or flux based on immutable laws of physics. Its validity is independently verified by comparison with an ionization gauge calibrated by the U.S. National Institute of Standards and Technology. Finally, we believe this may be important for all scientific and technological pursuits involving vacuum environments, including, for example, molecular beam epitaxy and atmospheric measurements. We invite you to read the paper.